Okay, so welcome back after the break. We now have a 45-minute Q&A session with the two teams that presented today, so ECO and CryoRad. So please don't be shy. Ask all the questions that are remaining after the first two sessions we had today. And so now we can start. Who wants to ask the first question of this last Q&A session? Yes, Hélène.
So I would like to go back to my question of this morning to the ECO team, because I didn't insist as much as Jonathan, so I didn't have fully the answer I expected. So it was about the diurnal sampling of and the impact of those on your mission, because it's really driving a lot of requirement on even the design of the overall mission with the two satellites. So can you detail what computation you have done starting from series in dataset, and what are the detail of the results? You said you started from this data and you did a lot of scenarios with various orbits, and at the end you obtained this number. That's what you answered this morning. So can you just detail the study and say more about it?
Torsten, that one is for you.
Yeah, so we start from observational data from Cirrus. They have the flux at 1 by 1 degree resolution every hour. And then we fly our satellites in orbit, physical orbits over that. And then from the point of the satellite, you look down and you have the footprint of the satellite, and then you integrate the flux that comes from that footprint. And you get one value. Right, that's the total outgoing radiation at that point. And then, let's see, what was your question? How that relates to the diurnal cycle. Okay, so for the processing satellites, what happens is you're not observing at a fixed time per day. It's processing through the diurnal cycle, okay? That does not mean you resolve the diurnal cycle one day. It means that over 1.5 months or 3 months or whatever, depending on the inclination, you will have sampled the whole diurnal cycle.
Yes, my question was that at the end you had the watt per meter square accuracy derived from this study.
Exactly.
So on the EEI, so can you go to this?
Okay, so once you have then simulated a year or many years, then you can calculate the EEI every year, okay? But you also know the truth in this simulation, right? The truth is the average of the Cirrus input data. It's not correct, but we use it as the reference, okay? So that gives us the...
Okay, and if you take into account the uncertainty on the Cirrus scene data set for the diurnal cycle, how does that impact your result?
Okay, so that's a good question. So the data set is based on Cirrus, which is the sun-synchronous satellites, but it also uses geostationary data. So it fills in the rest of the diurnal cycle with the geostationary data. I would say that is probably pretty good. You know, the shape of the diurnal cycle in that data is much better than what you would have, or much more realistic than what you would get from a climate model.
Yeah, for example, there are studies which show that in the Southern Ocean, there is strong bias in Cirrus diurnal cycle estimates and sampling. Did you look at that in detail?
No. But we did look in the tropics, so we have the GERB data actually, so that's where one place where we did compare. And it seems that Cirrus is much better than models.
And then when you say you explored various orbits, how did you do that randomly? I mean, you screen all the possible orbits and then, or did you have a strategy to explore certain orbits?
Absolutely. So the orbits that we have been looking at have either been sun-synchronous or polar, as we saw this afternoon, going straight over the pole. They stay fixed in absolute space, so you get 2 samples of the diurnal cycle per year, or 82, that gives you 4 samples per year, or 73, that gives you 6 samples per year. Those are the orbits that we have mainly been looking at. Once you have decided on an inclination, then you can also have a different orientation or insertion time. That's called RAN in these slides that we've been seeing. So we have then chosen 12 insertion times, so 2 hours apart, and then you can simulate those, and then you can combine different versions of those. And what we see is that you get the best performance when they are orthogonal, so 6 hours apart, basically.
And a final point, if we have only one satellite and you use the correction you build from series scene to correct the energy imbalance without having the data from the second satellite, what would be the final uncertainty?
Sorry, I didn't get that. No, but you said second satellite.
If there is only one.
Aha. Well,
you understand my question? Yes.
No, not really. I'm sorry.
If you do the reverse and you assume you have just one satellite,
yeah.
and so you measure it and you miss the diurnal cycle, but you know for the EEA estimates, but then you have observation from series scene and you parameterize the diurnal cycle variation and apply it to your data. What does it give?
Well, I don't have the answer to that, what it gives. I mean, you could maybe do that, and that would certainly be possible. But we want a system that gives us EEI by itself, not using auxiliary data, as we saw in the talk in the beginning. Once you start to do a patchwork of different systems, you have biases and issues with them that you are not in control of. So, well, in addition, you would have, still the issue with this inclined orbit that you would have very large errors regionally or continental errors that you would have to deal with if you were to make maps, for example.
Thank you.
Okay.
Thank you. Any other question? Yes, at the back.
Peter Schad from DLR. Also a question to ECHO. I would suppose that in 2036 we will have the opportunities of micro-launches. And since currently you have in your baseline the Vega launch with then a one-year drift phase, is it possible that with 2 separate micro-launches you can directly go into your target orbits, so to save time and maybe also budget?
Okay, that one is not scientific. I would love to, but I will have to pass the microphone to to someone else to answer that one.
Hello, hi. Thanks for the question. From the technical point of view, of course, you can do with 2 satellites. If this is the question. From the programmatic point of view, the micro launchers are today under development, and we need to have a baseline concept which is fitting with Vega. And sorry, my voice is starting to fade away. So I don't know if this answers your question.
Sorry, not really. Sorry, not really, because I think my question was if it's possible then to put the 2 satellites directly into their target orbit, because currently you plan for a one-year drift phase. So
the one-year commissioning wouldn't be needed because each of the satellites would be injected directly in their nominal orbit 80 degrees apart. And for the rest of the answer, you had it from Bernardo, yeah. Which says fuel for the delta V, etc., etc., etc.
Yes, Adrien Deschamps from CNES. I have another technical question for ECHO, which is related to the previous one, but more related to the platform themselves. If I understood correctly, The echo instruments are relatively small, and the payload is about 100 kilograms, something like that. And the platform are Copernicus-based platform, so around 1 ton or something like that. I don't understand why they don't have, you don't have any other alternatives platforms for echo. It seems possible to have a smaller platform for this mission, and it could also save budget obviously, I understand that there is a question of technical risk, and using already existing platform reduce risk. But seems it doesn't very wise to launch a very big platform for small payloads. So.
Okay, from the science, we would love to have additional passengers in the bus, but to make even more science. But that one I give to Bernardo as well.
Okay, thanks. Thanks for the question. First we need to understand certain things related to the platforms. One is related to the equipment and the quality and the standards for the equipment, and also the ones that are applicable for the Earth explorers, and also with the reliability related to all these equipment. Then the other is the design, actually, of the satellite, and also the size of the design. That has not only related to a small platform, but it is also related to, for instance, how do you deorbit, the space debris regulations, how much fuel you need to do certain things. So there is no one link of a small platform and we can do it. Of course, so there are multiple elements related to the quality, the standards, and also all other regulations, and also the different ways in which the instruments can be put.
Thank you. So any more scientific questions? Maybe some people who did not had a chance yet to ask a question. Yeah, Carla?
I had seen there's the upcoming NASA Libera mission, which is also measuring the outgoing Earth energy flow. So if you can maybe comment, it's probably a lower accuracy or maybe resolution, but NASA nonetheless is investing in it. So if you can just comment in relation to yours.
Well, certainly, and we have the chance to have one of the mission scientists of Libera in the MAG. So Libera is indeed, for everybody, a co-passenger of meteorological missions on the US side that will take the follow-up of the CRES that we have discussed before, with the limitations we have discussed, but there is more to learn.
So Jake Grissy from University of Colorado. So Libera is a continuity mission for the Ceres mission. So it's really a very different measurement concept to ECHO. It's a narrow field of view instrument that is scanning across the Earth and providing the mapping of the outgoing shortwave and longwave radiation. So that's important for continuity of the Earth radiation budget, but it does not provide an estimate of the Earth's energy imbalance, as is proposed with ECHO.
Yeah, and maybe to add on that, my name is Manfred Wendisch. I am from the University of Leipzig. And the difference is, as you just mentioned, we have a wide angle, wide viewing angle. And the point is that we are really put much emphasis on the flux measurements from the beginning. And that means we are avoiding this radiance flux conversion, and that makes a big difference. That's the major source of uncertainty for the flux measurements. If you don't use this wide field of view, then you are kind of, you have much more uncertainties in the flux measurements. And we start from the flux measurements. We need the high accuracy for the flux measurements from the very beginning. Otherwise, we are lost. We cannot resolve this 1 watts per meter square imbalance. And it's also, I would like to mention, it's also a first principle measurement. If we use these bolometric instrumentation, then we wouldn't need a calibration in principle. Yeah, and that makes a difference.
Okay, so I have good news. We have one question from online participants.
Someone's there.
Exactly, so it's working. So the question is from Adrien Martin from Noveltis in France. This is for CryoRad. So given CryoRad's capability to measure deep ice sheet temperature profiles, sea ice thickness, and sea surface salinity, how could its data improve our ability to estimate the timing and likelihood of the nearest climate tipping point, such as the collapse of the Greenland or West Antarctic ice sheets or changes in the Arctic Ocean circulation? And additionally, how might these improved estimates help societies better understand and mitigate the societal impacts of such tipping points, including rising sea levels, disruption to marine ecosystems, and changes in global weather patterns?
Okay, I will give the question to Steph, but it's a tough one for phase 0.
Yeah, so I don't know where I have to look to respond to the online question. So I'm Stef Limit from KU Leuven. I think our framing of CryoRad in the climate tipping point is really to indicate that our variables are really related to them. But many of these tipping points, it also really depends on the time scale, for example. So marine ice sheet instability is one of these tipping points, and we really don't understand where the thresholds of these tipping points are, or if it's a tipping system or a changing system at all. So I think what we will basically essentially do is really, in the spirit of Earth Explorer, is provide this process understanding of how temperatures in an ice sheet, if we measure them, they will provide a lot, and all the other variables we might derive from them, how we can understand the processes driving these ice sheets and their viscosity and so on. The same with the sea ice thickness. We measure this range of growing sea ice, which is a process which we still don't understand very well, and then we can go to the tipping point. So I think it's a long stretch to say that we will solve the tipping points. I think we will provide the process understanding to start better understanding these tipping points. And I see that Laurent also wants to say something.
Yes. So since we have for once a question on CryoRad, I would like to take the opportunity. So you think of the tipping point in terms of sea ice. All our knowledge now is based on climate models, which have problems in their realism. The problem for sea ice and ocean salinity in the Arctic, I can talk about the Arctic, is the knowledge of the cold halocline. The cold halocline has this layer, it makes the sea ice stable, and it will be there in the winter when there is sea ice. And now we know very little of how they get formed. We know the models, if you really inspect climate models for the cold halocline, you'll be very disappointed. So I don't also give a number of when we can reach the tipping point, but what I can say is that imagine that in the future we are actually worried about sea ice retreating very much. We would like to have predictability on a monthly seasonal time scale, and we know that the ice thickness is a precursor, is an indicator of predictability for the sea ice minimum. Then the halocline is also predisposing, as Jacqueline said earlier, the growth of sea ice. So the sea ice, again, will influence the weather patterns, as you all know by heart. And that's what will be important to plan, well, what will be life in the Arctic, although I don't know what life will be in the Arctic at that time. Yeah.
Thank you. So, Jonathan, first one question only, and then Vincent Henry.
Really? Okay, because tipping points came up and you mentioned it in your presentation, I'm going to press you on it. So the Greenland ice sheet, what's the driver of the tipping point there? And the West Antarctic ice sheet, what is the driver for the tipping point there? And how will end glacial temperatures help us solve both of those thresholds?
I think this is again for Anna.
It's what? Oh.
Yeah. For Anna.
Anna. Yeah.
Good.
Thank you. So it's different processes. For Greenland, it's the elevation feedback, ice elevation feedback. So this is melt. And of course, if you ice temperature will not be driving this in glacial temperature, but it will help us understand like how fast is the ice flowing and how is it thinning. So we contribute on that part. For the collapse of the West Antarctic ice sheet, it's a different process. It's more about the interaction with the ocean, what's happening at the base of the ice and the ocean interface. And no, CryoRad will not provide this, but it will provide the flow of the ice, so you can at least exclude that part. But there are other parts of the ice sheet where it will be important. For instance, if you look to East Antarctica, which has a different mechanism, it flows. There are some studies that show that, there are some frozen parts that's holding on to the ice shelves. If they're very close to the melting point, this is something we can see from CryoRad temperature. This would be something that can change the dynamics of these regions in the near future.
The PI would like to add a little bit to that answer.
Yes. Just to say that we don't touch the question of the ice shelves, which could be very relevant drivers for the Antarctica. But we know that for the collapse of Antarctica. But we know that using CryoRad, we are capable to doing something on that. We don't have time and resources for invest during phase 0, but it's a plan for phase A to investigate on this capability, because we know that we can, for instance, understand if there is marine ice intrusion in the ice shelf, and which can either fracture it and then can be the prevention for the collapse. But we don't have studied too much, but we are confident that we can provide information on that and then contribute potentially also on this item in Antarctica.
I mean, just because this question was raised and the two proposals are addressing different physical quantities, I would like to ask the ECHO team the same question, how this global measurement of the imbalance would influence our understanding about tipping points, because basically the system is always the same, we're just looking from different sides.
Okay, I'll hand over to Jochen.
This is really very difficult. There's one clear answer we could give, but where we have to hope that this answer never will become relevant, and that is the question, one cannot entirely exclude that the net climate feedback will turn positive from negative, which would mean the positive feedbacks would overwhelm the negative Planck feedback. ECHO would see that. It would mean the end of the world, so literally, Earth would turn into something like Venus if that happens. So that is something one really has to hope that will never become relevant. But ECHO would see that because we will be able to determine the sign of the climate feedback. At the less dramatic level, it's quite hard to say, because even though the many of these tipping points, they take up a broad room in the public discourse and also in the scientific discourse. But if one is honest and realistic, much of that is speculative. So it's really very hard to say what can be done in concrete terms, because most of the tipping points that are being discussed are beset what is technically called deep uncertainty. So it's hard even for many of them, Greenland ice sheet being the exception. There it's fairly straightforward, but for practically all others, the uncertainty is so large that it's even hard to say what the appropriate conceptual model is for it. So that's harder to say. I'm sorry.
Henri?
Yes, I have a question on CryoRad. Actually, it's the same question as Jonathan this morning. The difference is that I'm not an expert on ice sheets, but I didn't get exactly the answer about how the information about the base temperature of the ice sheet will really make a big advance in terms of modeling. Because what we've seen in the report is that, okay, you do in model intent comparison, there are differences which translate into wider differences, but I didn't see evidence that by constraining this one parameter, this will really bring, or this is one of the key parameters that will shrink the difference between models. So I reckon it's only phase 0. So I would like to know a little bit more about your precise plan for phase A, so that how the modeling that would be done on purpose or OCs could really demonstrate more that this is something that will bring an advance for this science.
I give it to Anne again.
Yes. Okay. So I don't know what we have planned for phase A, but this is definitely something that, yeah, I guess we would be very good to look into. So for an ice sheet, it moves both by deformation and by sliding. Today, when you have to find out whether the ice sheet is sliding or just moving by pure deformation, you use you have to infer it. So you use datasets, some datasets of the surface. It's a very well known parameter. You use, for instance, ice velocity to constrain the flow. It has a little more uncertainty, and it also varies through the year. But you use these two measures and the ice thickness, which is to some degree known, but has very large uncertainties in other regions, and then you invert for the basal conditions, given what you assume about the viscosity inside the ice sheet. So knowing exactly where you would expect sliding or where sliding could happen would be a constraint on how to initialize your model and what the state is today. And also knowing in the regions where we are close to the melting point, so it's still frozen, but we're close to the melting point. This is a game changer if there's some regions that help keep back the flow of the ice and keeps it from accelerating. But if they suddenly, because of changes in flow in the kind of near future, that could change the flow. So knowing what goes on at the base is a very important parameter for setting up your ice flow model.
Any more questions? Yeah.
Yeah, Annette Bartsch, BGEOS and Argeo. I have a question for ECO. So you have 5 different sensors there. For the Earth and the solar radiometer, and then the WIS, sphere and tear instrument, and these WIS sphere and tear instruments, as far as I understood, you need them to understand like regional contributions. And if I understood correctly, it's also useful to fill this polar hole gap. But what I wonder is, for the energy imbalance, how important or how crucial is it to have these with sphere and tear instruments on the platform?
So here we're talking about interpreting the variations of the EEI with the specially resolved information of the different fluxes, short and long wave. Torsten, you take it?
Okay, so for the measurement of EEI, you're correct. We are only now planning to use it to fill the polar gaps. But to understand why the EEI is changing, we need to have the spectral information, long wave, short wave, and spatial information of where that change is coming from. That helps us tell things apart, like aerosol forcing or clouds or volcanic eruptions or solar radiation management, those types of things. So, and by taking advantage of the common viewing geometry, we can really make that other product much stronger by anchoring it on the radiometers. Does that answer your question?
Okay, maybe I have a question on ECO myself, actually, following along these lines. What happens if in the end you don't reach the 0.7 watt per square meter you have? Can you still use the mapping that you will do with all the channels to nonetheless learn some things about well, the radiative budget in itself? And second related question, you have a goal, you have a threshold value. At one point, do you consider that the EEI measurement you have after 1 year is not enough to be the reference to reprocess and put in perspective the 20 years before that?
Okay, so two parts of the question. The flux maps first, which is related to your question. Maybe just to add quickly, we have flux maps from other missions. ECHO is about the mapping of the fluxes. It's not a process unlike EarthCare and other such missions. This is really the mapping with a consistent radiometric anchoring together with the EEI. Whereas in the system we have, they come from different missions, different radiometric calibrations. So that's a very important thing of the mission. So yes, there's a lot we can do with the flux map. So for that, I'm looking who I'm going to pass on the question. And to the second leg of the question, which was about the EEI, what if we are at 0.3 or 0.7? What is the kind of science we can advance? The kind of questions we can address? We heard a little bit of that this morning with Joachim. Having the sign of the EEI already with certainty, 2 sigma, is something we don't have today. So that's, I don't know, Joachim, if you want to complement that later. So for the flux maps, you want to take it, Jackie, with the experience of GERB?
Question is are the flux maps useful if the EEI measurement isn't accurate enough, yes?
Yes.
Not really. The point is to anchor them to the accurate EEI measurement. That's the new thing. So along their own, they would obviously be not nearly as accurate without an accurate EEI, and they wouldn't be offering anything new.
And about the performance, so let me be clear, if we don't make it at the level of 1 watt per square, if we do it at 2 watt per square meters, we're back at what we have today. I mean, it's like serious. So if we are at the level of 1 watt per square meters, then we will probably have the sign of the EI, which Sirius doesn't have, which is already something. But that's not what we are chasing at. I mean, we really want a few tenths of watt per square meters. 0.7 is already something quite good because we can constrain the global fluxes of the energy cycle. And then we can have all these different science questions we can address with a level of uncertainty. Much better than what we have today, that's for sure. But then, so yeah, we have to be at those 0.7.
Thank you.
Maybe I will just add to that. So for us, for climate science, this is the equivalent of detecting Higgs boson, right? We are really trying to, verify the 200-year-old theory. And if we cannot do it, even the sign of the imbalance, then there's no point, really.
It's really about detecting and quantifying. Right? Detecting is 1 watt per square meters, and then 0.7 you start to quantify. And that's what we want to do. I mean, we are closing the energy budget. It's about physics. We need to quantify and to have uncertainty and to be able to test theories and say, well, it's right, it's wrong, and what's going on.
Yeah, fair enough.
The climate Higgs boson.
Any other question on either ECO or CryoRad? Scientific or technical? Yes, Elsie.
Hello, my name is Elsie Swinen, also part of ACEO. I have a question for ECO. So I understand that calibration of the instruments should be very precise. Could you elaborate a bit on that? Because I saw in the report you rely also on vicarious calibration that has a certain uncertainty budget associated with it. So I'm not sure that I understand well the reasons for that.
So the vicarious calibration is with reference to the images, mission objective 2, the flux maps. It's not about the radiometers and the EEI, mission objective 1. Are you interested that we talk about both, about one in priority?
I think it,
the
in general, I think it requires a bit more elaboration.
Okay,
calibration.
so the radiometer we talked about this morning, the traceability to the SI standards, etc. So maybe we focus on the second leg, the mission objective 2 for now, and the vicarious question. Okay.
Yes, so I'm Steven de Witte from Royal Observatory of Belgium. So for the vicarious calibration, specifically for the shortwave, and it's based on experience with existing shortwave instruments. And yeah, many shortwave instruments have onboard shortwave calibration sources, which is not for absolute calibration, but for stability. And experience simply shows that vicarious calibration, just looking at stable targets on Earth, often provides more accurate results for the stability than onboard calibration sources. One example of that is the MODIS instrument. Another one you know quite well is the ProbaV, Polder. There are a lot of examples on that.
Yes,
just like the technical difficulty of the onboard shortwave calibration is technically quite difficult.
Yes, but the models to do the vicarious calibration come with a certain uncertainty. So my question is rather about that.
The number I have on my head for MODIS is like 1%. And that is better than what most of the onboard calibration sources get.
Just to put it a little bit in context, the vicarious calibration of the images doesn't really impact our products. It's really just to sort of show that the images are roughly at a good starting measure. The actual calibration of the map fluxes will come through intercalibration with that wide field of view measurement. The wide field of view measurement is an absolute measurement. You know, it uses the same standard that you would use in metrology labs to show traceability between a watt and the heating. So it's a real absolute fundamental measurement. And that is the thing that underpins the calibration of the images in the end, of the fluxes in the end, which are derived from the images, and underpins the calibration of the Earth energy imbalance. So yeah, the imager, sort of, that's just like a first pass that you do for vicarious calibration.
Follow up this question. Can you explain me there was a concept called CryoRad at a certain time, which was supposed to do absolute measurement of radiative. Can you explain the parallel and differences? I don't remember exactly.
There was even a concept called truth. With a successful PDR, which ECHO is inherited a lot from. We heard it this morning, and unfortunately not continuing. But maybe I pass over to pass it to Jackie again. Yeah.
Well, but I will just quickly start with saying, compared to truth, which is a similar concept, it uses the same measurement concept of being an absolute measurement. It will have slightly more noise on it. It's not, cooled. It's not trying to make that whole spectral measurement that truth was trying to do. But it is underpinned by the same measurement technology, an absolute in the shortwave. So there's that, and I think...
No, I think that was it. But one thing we can recall maybe, and you can help me in that, there is the absolute accuracy of the sun, the absolute radiometer, the absolute radiometric accuracy of the Earth. What matters for the EEI the most, I mean, each absolute individual is important, but is the relative radiometric accuracy. And this is what was described this morning. Okay? It's because this is what will lead us to the EEI in the end.
I believe the discussion we had amongst others, you understand that very well, but we need to be convinced of the accuracy that you obtain. And repeating the same thing doesn't convince us, just to make it clear.
Well, then I will look at the... Luca, yes. Luca, yeah. So he give you more details about what has been done with industry under the scrutiny of ESA.
So I will first recall the information from this morning, and then I will add you more information about the calibration. So to measure the total uncertainty, the residual error between the two radiometers, you first do an error budget for each of the radiometer with about 35 terms for each of the radiometer. You measure that in ppm. You take into account all the optical, thermal, electronics noises, stray light, thermal environment, optoelectrical inequivalence. For some of them, we have dedicated risk retirement activities for the acquisition mode, for the Earth radiometer, and for the optoelectrical inequivalent, because we have a higher, bigger cavity. These are one thing. When you have something similar, your errors for both radiometers will not cancel completely, but will be reduced in the differential error. In the end, you have this budget, and this is how you find that in uncertainty, total uncertainty on the level 1 product. Now, to go further, how do you measure that in practice, that you can reach that value? And this is related to the calibration method. So, because indeed it is challenging, it is a very small quantity, so we need to develop these calibration aspects. We had a risk retirement activity, another one on the calibration method, to separate all the different terms that we want to calibrate, the coating, different calibrations to do on the coating for the full spectrum, also depending on the angles, the angle on incidence of your laser. During that, on the cavity coating, so first on a flat sample, and then you do that on the cavity. Also to calibrate the electronics and to measure the thermal regulation of your cavity. All of that, we have plans for that. We have identified what to do for the calibration in phase A. The calibration is not done already, but we have already the roadmap for phase A to calibrate this value. So indeed, this is we have this simulation that shows the total uncertainty, residual uncertainty. We have already a breadboard on the acquisition mode for the continuous mode with a PMOD, and we have identified all the calibration methods that we need to do in phase A. Once we have a breadboard, we would go, we will tackle that. Does that answer your question? Thank you.
Marcus?
Thanks very much. And I think I understand that part on what you can do before the mission is actually flying. And here, yeah. But once the satellite is, or the two satellites are up in orbit, is there any means to check whether the calibration is actually stable and still in place? Or can you only infer that from, I mean, plausibility of what you will measure? Is there any independent means to double check on your calibration once the instruments are in orbit?
Okay, we'll have the chance to have two satellites already, so they can look at the same source and intercompare, and more details will be provided by Margit.
So we will have, so the radiometers have 3 channels, as we heard this morning, and one will be the nominal channel, and one of them will be the backup channel. So this is a means to track degradation. This is not fully independent, but it's a separate channel, an independent cavity that can track degradation. And it's both on the solar radiometer and on the Earth viewing radiometer. This is one thing. And then I should say we also have a lot of flight heritage already for the DARA instrument. This is already in space on the Proba 3 mission. So the absolute accuracy of these of the solar instrument alone is at 0.5 watts per square meter. So for the incoming solar radiation, this is then at the level of 0.1. And but of course, I mean, typically, currently we have 3 operational TSI radiometers in space. How the future will look like, we don't know, but even from the current situation, we know how the radiometers perform, and the echo radiometers will certainly be an advancement in accuracy. Yeah.
And to add on top of that, so indeed we have the 4 radiometers, 2 per satellite, and for each radiometer, the third cavity is there for redundancy and long-term monitoring. But you can also use the Earth radiometer. You can flip the satellite to look at the sun to have an inter-comparison between the Earth one and the solar one. So you have, let's say, on top of that, you have many ways to intercalibrate that.
So a lot of self-consistency checks still possible in space. Yeah.
So thank you very much for these answers. I'm afraid we have to stop here because we have reached the 45-minute limit already. So thank again to both teams for answering the questions and to all the audience for asking the questions. So thank to all. And I hand over to René.
Yeah, I'll ask the team to sit a little bit just to make it faster. I hope that you're still comfortable on those chairs as well. Phew. I don't know if you're still hungry for more science and technology, but I think for most of us these have been 2 absolutely remarkable days. First of all, I'd like to wrap up a little bit on the statistics. We have been very close to 200 people in this room. And although the people online were a little bit more quiet with the questions, they were also numerous, close to 100 people on both days, actually. So this is something that shows a remarkable interest in what is happening here. Broad interest from a large variety of user communities, the different types of scientists that are interested in what we are doing. I don't know if we plan to publish statistics on that, but at least we see very strong participation from the entire European Earth observation community in this activity. For us at ESA, I think we are absolutely stunned and delighted to see such an incredible quality in the presentations, in the preparation, and we have deep respect for all the work that has gone into what we have seen here in these past 2 days. You show the power of Earth observation in Europe, you show excellency, and I think that this is what it is all about, what we're doing here. And I think we could deserve to give all of ourselves a kind of a nice hand of applause for that, because it is really, really important that we managed to do this and we have pulled it off. And as someone said yesterday, we should all be proud of wearing the Earth Explorer patch. We don't have one, but if we would, I think we will have handed out one to each and every one of you the moment that you exit this door, because I think the Explorers are something to be proud of, and it's something to be proud of also to be part of this family. So I'd like, first of all, to give us all an applause for all of this. Now, this closing session is also about the next steps. Of course, the HAO is here. They have been listening, they have been asking questions, but the real hard work starts, I do not know, tonight, but at least tomorrow morning, we will see. They have a task, and if you have read carefully the Earth Explorer 12 call, you will know that the task of the Advisory Committee on Earth Observation is, first of all, to provide a ranking, and this is written explicitly in the call, and secondly, to come up with a recommendation towards the executive for up to 2 missions to proceed into phase A. Now, we do not promise, but in line with the tradition that we have, it is the intention of the executive to provide to the proposing teams the outcome of the deliberation of the HAO by Friday, late afternoon, maybe it will be early evening, we will have to see, but that is the intention. It is not a promise because the ACEO still has to do all their work, but this is our intention and this is what we would like to be able to do. Also to maybe take off some steam from a highly tense period. Yeah? So based on that, it is then the task of the executive, that is a nice word for ESA, to formulate a proposal to the member states and to the Program Board for Earth Observation for a proposal, let's say, for the down selection formally of these 2 missions. And our job at ESA is to provide that recommendation to the delegations, to the member states in early September for formal decision during the program body in September, which is planned on the 24th and on the 25th of the month. So this is the time when we expect a formal decision for the down selection towards phase A. And then, of course, after that, when the process is well underway, actually, the next time we will meet in a forum like this one is in about 2 years, where we will be discussing the real selection for Earth Explorer 12. It will probably not be in Tallinn, but it will be the same time of the year in 2028. So this is what is going to happen. Still, I have some more tasks to do. First of all, I'd like to report that we have a little bit of a casualty from the visit to the restaurant yesterday, or to the Fotografiska. When we left, there were 2 jackets that did not come with their rightful owner. At least that's what we believe. So if some of you is missing your jacket, we have 2 of those, you should let us know. Otherwise, we are formally delinquent because it means that we have stolen 2 jackets. Yeah? So that's the first statement. The second statement I'd like to make is that for some of you, actually many of you, there is a celebration event also tonight. You may wonder what your blue, not everyone has that, but if you have a blue dot on your badge, it means that you're formally recognized as having contributed to the reports, to the preparation of this meeting, and then you're also invited to a celebratory dinner tonight. And for that, the bus will leave at 1800 sharp, again from the same place as yesterday. Unfortunately, no blue sticker means no food. Yeah? Then, 2 more things. I'd like here to thank, first of all, formally, also from the side of us here at ESA, all the proposing teams, the mission advisory groups, the technical team, the science team, industry, all the participants here in the room, the delegations from member states. Actually, we are very happy to have seen many delegations here in the room. It shows their great interest in this part of the program as well. The Estonian Space Office, the city of Tallinn, and of course, the hotel itself, all of the organizing people who have been here. We have the lead organizer on our side here in the back of the room. Her name is Francesca. She is here with colleagues, and I think we should all give them a very nice round of applause for the excellent work that they have been doing here. And with that, it rests me nothing else to say than safe journey back home. As we will keep our promise, just like you have done, yeah, and the process will continue according to plan. And thank you again for supporting Earth Explorer 12. Thank you again for supporting the Earth Explorers. And thank you for being such great ambassadors for Earth observation in Europe.